Okay, so here's our wrap-up video. Oh, I didn't go far enough back. So today we were talking about just reviewing the inverse Laplace transform, making sure that we all feel okay using the linearity property with it, and then most importantly, how this applies to differential equations. So I said that we would do a couple linearity examples, learn a derivative rule, and then actually look at solving initial value problems using Laplace transform. So there was our recap of what we know about Laplace transforms in linearity, and I said we're going to use this property a whole lot. So we did a couple examples of the inverse Laplace transform using the linearity property to make sure that we all feel comfortable with given a random thing that we have to take an inverse Laplace transform of, can we rearrange it so that we can use our Laplace transform table to find that inverse? And hopefully you feel better about that after looking at those examples. Then we learned the rule for taking Laplace transforms of derivatives. We wrote it in the general case for some function f, and then we did a couple examples using derivatives y. This is also something we use a lot, so hopefully filling in these steps for how to take L of y triple prime, L of y double prime became more obvious as time went on. And then we talked about how we actually solve initial value problems using Laplace transforms. And the basic idea is that we take the Laplace transform of both sides. We have a lot of little tricks to remember. We have to use linearity, we have to use our derivative property, we have to plug in our initial conditions. But eventually that leads us to something that has no y's, t's, or derivatives left. And when we set both sides equal to each other, we have an algebraic equation to solve for y, capital, equal to some stuff. And then we just have to take the inverse Laplace transform of both sides, but that tends to be the longer part of the problem just because there's a lot of algebra. We have to use our linearity property. Oh, and then at the end, there should be no s's left because we should be looking at a function of time. So we did a couple examples. The first one, we sort of went through all those steps I just said. We took the Laplace transform of both sides, y prime plus 3y and 13 sine 2t. And then we set those sides equal to each other, and then we solve for capital Y. And then we wanted to take the inverse Laplace transform of both sides. The left side is always easy. We just have y of t. But the other side was difficult. We had to do this big, long thing where we did partial fraction decomposition so that that right-hand side looked like something that we could take Laplace transforms of. But after we did that, the actual taking the inverse Laplace transform part didn't take too long. And I did another example, which followed the same steps. And I didn't show all the algebra in the middle for this one because hopefully, you could follow through that on your own. And we just wanted to emphasize the important steps for how to solve differential equations using Laplace transforms. That's the thing that's new to you. And so I wrote right here the wrap up where I said that we practiced with inverse Laplace transforms using linearity because that's important. Taking the inverse Laplace transform is how we get to the solution y of t in all of these examples. So we need to be able to do that accurately. And then I summarized the steps to solve initial value problems. You take the Laplace transform of both sides. You solve for big Y equal to some stuff. There's a bunch of algebra involved. And then you take the inverse Laplace transform of both sides. And that gives you little y of t equal to some stuff that doesn't have s in it anymore. So your practice problem for today is to solve the initial value problem right here. Y prime minus y equal to 1 with y of 0 equal to 0. And you could solve this using exam 1 methods, but I want you to use the Laplace transform to practice that new tool. So work on that, and then I will see you in class.